Thank you very much, Tim, and thank you everybody for coming this morning. Judging by the sounds coming from the bar last night, it's impressive that people have turned up. Okay, yeah. So as Tim said, I'm going to talk about interpretable machine learning for materials design and characterization. But before I go into the talk, I'll just give you a little introduction to where I'm coming from. So I'm coming from the Rutherford Appleton Laboratory, which is just about 45 minutes or so north of here, just south of Oxford. So we have, it's a national facility, synchrotrons, lasers, things like that. We're also responsible for things like the particle physics data in the UK that comes from CERN, and Jasmine environmental data as well. So there's a lot of data at the RAL site. And just to give you an idea, nowadays with the increased detector speed at some of these facilities, so a single X-ray tomographic experiment now at Diamond Light Source will routinely generate about 100 terabytes of data. And since there's nothing like some obsolete technology to make you feel old, I decided to convert that into these 3.5-inch floppy disks. And I think that's about 69 million 3.5-inch floppy disks, which I did a very quick back of the envelope, and I'd say someone can check this quite easily. That should be enough to get from London to New York. So you can't kind of do things the way you used to, where you go and do your experiment, take all your data away with you, and then spend some time analyzing it. We need ways to treat this data efficiently, and that's kind of the modus operandi of the scientific machine learning team. That's kind of why we set up this team and are trying to apply machine learning at these national facilities. So yeah, what I'm going to talk about is actually, a lot of the work is actually going to be machine learning for simulation as opposed to on that experimental data, but some of it will also be to do with the experimental data from the neutron source. But why is interpretability important in these applications? So there's obviously this XKCD comic on the right-hand side, which is a kind of general view of what machine learning is, some kind of black magic where things don't work, you just stir it around a little bit more and until it starts looking right. And we don't really know what's going on. But I want to say that that's not really the case, and if we look inside the models, we can actually learn something from them. We can learn what's going on. And that's really important for a number of reasons. So when the models are underperforming, that helps you diagnose why the models aren't working. And that's, I'll show an example of that in the first instance that I show. When the models are actually performing as well as humans, then it really helps to build trust if you're able to say why it's giving the result it's giving, and that makes sense. So the second example I'll show has quite a lot of that involved in it. So that was working closely with people from the ISIS neutron and muon source. And I mean, I could produce models quite quickly that gave the right answer, that were telling them what they thought they should see. But then they just weren't happy with that. They were just, well, why is it saying that? They just wouldn't trust me. It's like dealing with a 5-year-old or something. They just keep asking you why. So it's really useful for building trust in that sense. And then the final thing, and I guess this is something that, unfortunately, my third example won't show this, but this is something that I think would be something really cool to show, is when models start to outperform human level, we could interrogate them and understand what the model is doing and potentially learn new physics from understanding why the models are performing so well. Okay, so before I go into the examples, and apologies to those for whom this is obvious, but I just want to draw a bit of a distinction between deep learning and classical machine learning, because it's somewhat important in the types of interpretability that I'll apply during this talk. So in traditional machine learning or classical machine learning, we spend a lot of time building meaningful features before feeding them into the model. So I've got the example here of 2 pictures that we want to classify. And say I wanted to put that into something like, maybe I want to put that into a decision tree or something. I would probably spend some time annotating it and tabulating it and making notes of things like the number of eyes in the picture, does it have whiskers, does it have legs, and so on. And those kind of tabulated data that I've spent some time building features for get fed into the model, and then it makes a decision. Whereas if I do that with a deep learning model, like a convolutional neural network, we really use pretty unstructured data. So we literally just feed it the picture. So it learns from all of these pictures. And it's kind of said that the deep learning model learns the features from the data. So it learns to extract meaningful features from these pictures. So it requires a lot less manual input, but in general, it requires a lot more data. And then when we have those features, we feed it into some kind of classification model, which can be anything, and it does the classification. So yeah, the first example I'll show is predicting dielectric constants for materials, and this is using classical machine learning. So dielectric constants, it's for anyone who's not chemist or physicist, it's a measure of the response of a material to a field. So there's many different, it's not really actually a constant, it should be the dielectric function. But what we're interested in is actually the high frequency part of the dielectric constant. It's really important for things like LEDs, optical fibers, photovoltaics. So it's a property you'd like to be able to predict for a material to understand if it would be useful for these kinds of applications. But it's difficult and expensive to measure, and it's also relatively difficult to calculate from first principles. And so if we would like to do large-scale screenings of materials databases or so on for dielectric constants, we'd like a quick way of being able to calculate them. So the idea here is, can we build machine learning models to do this? And I should say this work is mostly being done by Kazuki Morita, who recently just graduated with his PhD from Imperial College. So first thing Kazuki did was to go and build a bunch of different machine learning models for predicting dielectric constants. And he compared them against each other, as you do, and found that support vector regression did the best job, does a reasonably good job. Some cases it fails, and that's the kind of result, this is by far the least interesting part of the paper, was that he was able to actually build a model. What became much more interesting was understanding what the model was doing. And to understand what the model was doing, Kazuki applied a method called Shafty analysis. So Shafty analysis actually goes back a long time. It's back to the 1950s. And it's a method for understanding n-person games. So it comes from game theory. And essentially what we can do is treat our model as a coalition of players playing a game and look at how different combinations of players give different outcomes within the game. And what it is it's a way of kind of a principled way of assigning values to the contributions of different players in the game. So it can be used for all sorts of things. So you can use it to assign values to what a certain person has brought to, say a new startup company, and you have a bunch of people who've joined it at different times, and you want to work out how much the engineer, how much the advertising person has brought to it, how much the salesperson has brought to it, and so on. And I'll just give a simple example here of 3 individuals go out for a meal, and the bill comes to £90. Now, they've done things like they've shared a bottle of wine, they've shared some sides, they've got some bread, some of them have got desserts, some others haven't. And it's got messy, and they don't want to go Dutch. They want to really understand how they should split this bill in a fair and principled way. So these are really fun people to go for dinner with, obviously. They want to split the bill in a principled way. So what you can actually do is, if you have a model, which we do, we have some kind of machine learning model, we can model different scenarios. So we could model where just Alice goes for the meal, and we find that it costs £80. Then just Bob, and it's £56. Just Celine, and it's £70. Then we can look at combinations of them and see how much it is for each combination. And by doing that, what we're then able to actually do is build up this table on the right-hand side here, where we look at different orders of the individuals coming to the meal. So if it goes A, B, C, so we know that Alice alone would build up a bill of £80. Alice plus Bob would be also £80, so the contribution from Bob there is 0. And then Alice, Bob, and Celine is 90, so there's a contribution of 10 from Celine. And we can do all the permutations of that and build up this list, and then by taking the average across each of the columns, you get this you arrive at this figure for how much each of them has contributed to the bill. And so, okay, that's abstract. That's for some kind of a bill splitting scenario. But we can do the exact same thing with our machine learning model, because we've got all of these properties or these features that we have fed into the model that result in the prediction of the dielectric constant at the end. And so this plot on the right-hand side just shows you some of the features. So you've got the density of the material, the amount of oxygen, the band gap of the material, formation energy, and so on. And you can see how they each contribute to the dielectric constant. And so this is actually, if your mind is working really quickly, you might realize that because obviously there's a lot of permutations involved in the Shafty analysis, it would actually become combinatorially impossible to do. But there's this recent work on approximations to Shapley values, and this SHAP analysis. So it's a tool that you can just pip install and essentially run your models through this SHAP analysis, and it produces these nice plots like this one on the right-hand side that show you how the different factors contribute to the final output. And so we can do nice things with that. So we can look at things like, so this is, Kazuki was looking at how his machine learning model compared to kind of classical models of dielectric constants. So this is the Penn model at the top. And what Kazuki plots on the left-hand side here are the results from his Shapley analysis, where you've got the Shapley contribution on the y-axis. So if it's positive, that means that the factor is increasing the dielectric constant. If it's negative, it's decreasing the dielectric constant. And then he's got the band gap of the material on the x-axis. And you see this inverse relationship between the band gap and the dielectric constant, which is exactly what you get in the Penn model. And then he's also plotted the materials density, and you can see there's kind of a confounding between the band gap and the materials density. So they both contribute to the final dielectric constant. And again, that matches up nicely with the classical model of the dielectric constant. And then what he's also able to do is look at this point down here at the bottom, which is circled, which the model performs particularly poorly for. And then this plot, this kind of bar plot on the right-hand side of the screen, that's showing how different factors have contributed to that final output. And you'll see there's a huge contribution at the end here from the materials density, and that has contributed negatively. So it has a negative SHAP value, so it's pulled down the dielectric constant, so resulting in this low value. And we can actually look at the distribution of the densities of materials in the training set, and you see that this one here is kind of, it's a material that's very much at an outlier in the kind of density distribution. So it comes from a sparse region of the sampling, and that gives us an insight into why it is, and kind of the limits of applicability of the model. So you might want to say that this model is something you maybe don't want to trust too much if your materials density is not within a certain kind of region. Okay, so that was an example of doing some interpretability on classical machine learning. I'll now look at deep learning. And in this case, we're looking at, so this is neutron data from ISIS, and it's a model to identify which magnetic Hamiltonian a material has. So they measure inelastic neutron scattering. You get this kind of signal in the middle. And from that, somehow you're meant to be able to decide between these two different competing magnetic models for the material. And so the first thing that we did with this was to go and train a convolutional neural network, which takes the data in, and obviously with that, it does the feature learning, and then makes predictions about which class the material actually belongs to. And it does quite a nice job. Eventually, it gets 96% accuracy on a test set, and we were able to, after a little bit, get it to work correctly on the experimental data as well. And that's great, but again, the more interesting thing is, why does it give this answer? And to understand that, we turn to a method which is called class activation maps. So I'm showing a picture here of something that's classifying the gym equipment in a picture or something, and it's saying this is a barbell. And the class activation map is then trying to say which part of the picture is responsible for making that classification. So you get these kind of heat maps at the bottom that show you why it said barbell. And we thought, okay, this is cool. This seems like something we could use for understanding our neutron data. And so how class activation maps work. So essentially what you do is you do this representation learning part with your convolutional filters. And at the end, the final layer of convolutional filters you have here, and they have some kind of weights associated with them. And then you also have these filters. Each of them contributes a certain amount to making one or other of the classifications at the end. So these lines here represent the weights. So what we do is we take the product of each filter with the weight that it contributes to making a certain classification. And then you just take the average across. So these sharp arrows are meant to depict it being the average across all of the filters. And you come up with some kind of map which shows how much those different pixels were contributing to a classification. And then you project that back up onto the original image. And so here we are doing it for the neutron data. So this is the original data on the left-hand side. It passes through the model, makes the correct classification. Then we produce these class activation maps. And I've actually coarse-grained the map. So each of these squares in the image on the left-hand side, the small squares are kind of slice through energy and Q space. And we want to know which slices in energy and Q space are important for the classification. And it kind of comes up with a few that are most important for that classification. And the really nice thing is, so this data had been interpreted several years before, so we were kind of using it as a fruit fly experiment. But the really nice thing is that the convolutional neural network was looking at exactly the same part of the spectrum that was used in the PRL paper from several years beforehand to actually distinguish between the two different models. And what's nice about that is that it means that you can take this kind of really complicated data, lots and lots of data with lots and lots of signals in it, and you're looking for a needle in a haystack, kind of the signature of what determines which magnetic structure is the right one is a really small part of that data. And typically what you would do is a PhD student would spend 2 or 3 years slicing through that Q and energy space, running some simulations, comparing the simulation to the experiment, and working out which one best explains it. And what we're able to do here in a really short amount of time using the convolutional network with the explanations is say, okay, it's these areas of Q and energy space that are really important for distinguishing between the two magnetic models. And there's also, there's a paper there, there's also a GitHub repo where you should be able to, if you're interested, you can download the notebooks and so on to reproduce the work in that paper. Okay, so finally I'm going to move on to some work with graph networks. So this is more about uncertainty quantification rather than interpretability. But just quickly to say graph networks, what they are, why they're important. So graph networks are becoming increasingly popular as ways to model materials. So you essentially can model the atoms as nodes in a graph with the bonds as edges in the graph. And you can have some kind of function, which is usually a neural network, which passes messages between the nodes. So you have your vectors at each of the atoms, and they update each other depending on how they're connected. And you can learn the weights in those networks. So you learn how different types of atoms interact with each other. And just to show this kind of leaderboard down here at the bottom is just, it's the MatBench, which is a materials benchmark for simulations kind of benchmark suite. And I'm just showing here that for the majority of the properties on this now, graph neural networks are the top performing models. So they're becoming increasingly important for predicting materials properties. So these deep methods are really powerful for predicting properties, but there are also some worrying failures. So the example I show here is a kind of famous one of adversarial noise. So we've got a picture of a panda, and your convolutional network is predicting that it's a panda with good confidence, working fine. And then I sprinkle a little bit of noise on top of it, and the resulting picture still looks like a panda to me. But suddenly the convolutional neural network is confidently saying that this is a gibbon. And that's a little bit worrying, that the model is so kind of fragile and so susceptible to small changes which shouldn't change the output. So, you know, we worry a little bit about this. And some of the reasons that they do this, well, in classification, we train models to be overconfident to some extent, because we use sigmoid functions to separate out classes. So when you see this 99% confidence or something, it doesn't really mean 99% confidence. It's been separated out with a sigmoid function. And if we're doing regression, we tend to take just a single neural network. But actually, if you look at the parameter spaces of neural networks, they're very shallow with lots and lots of local minima. So you could have lots of neural networks with different parameter sets that could give correct answers. And you're taking just one of them. So how can you trust that, just that one number? So we're interested in how can we put uncertainty quantification on the network. So there are lots of methods already existing that do uncertainty quantification. And in material science, a particularly popular one is Gaussian processes. Well, I won't go too much into how Gaussian processes work, but they're really powerful, useful method. And the nice thing is that they give you an uncertainty quantification with your prediction. And I just show an example here from a nice paper where people are predicting, I think they're predicting some kind of spectra with a Gaussian process, and it has these confidence intervals on the prediction. But the problem with Gaussian processes is, like classical machine learning models, you generally need a relatively low dimensional space, and you need handcrafted features that go into that low dimensional space. So what we've tried to do, and I should say this work was mostly done by Johannes Alate. So Johannes was a PhD student who came for 6 months to the Rutherford Laboratory. He's actually a PhD student in astronomy, but picked up the material science extremely well and did a really nice job on this project. And what we've been doing here is combining the feature learning of the deep learning models with the uncertainty quantification of the Gaussian process. So in a standard graph network, what happens is the structure goes through the graphs, it gets featurized to this vector at the end, and usually you pass that to another neural network, a feed-forward multi-layer perceptron or something, and that makes your prediction. So what instead Johannes was doing is pass that to a Gaussian process. So then you get your prediction with some kind of uncertainty quantification. And the first thing he did was just to look at, does this vector that comes out of the graph neural network, does it have some kind of correspondence to the final property that you're trying to learn? And that was formation energy in this case. And you know, these are like some kind of psychological tests, these dimensionality reduction. But you can see structure in them, and to some extent you can see that it does correlate with the energy. So we have some confidence that it's a reasonable thing to use. Then actually use the Gaussian process from the graph network features to make predictions, and it does quite a good job. 0.3 milli-electron volts per atom mean absolute error, which is comparable to the best graph neural networks, a little bit less, a little bit of a deterioration in the performance, but we would expect that. But what we get in return for that deterioration is we get error bars, and so I'm plotting here the 2 sigma confidence. So with 2 sigma, 95% of the points should fall within the correct value. And at the bottom, you have the errors, or the predicted uncertainty versus the errors. And that kind of highlights that there are some regions where it does particularly poorly. Okay, I'm getting my 5-minute warning. Excellent, thank you very much. So we've now got this confidence prediction, but actually we can go a little bit further with that, and we can actually start to use that to do active learning. So we know that we need lots of data in general for training these deep learning models, and sometimes the data is expensive to get. So we'd like to be able to choose the best data for training the model, and that's kind of what active learning is about. So what we do is we train our model on some expensive to acquire data, We run it through, we make the predictions, we get the uncertainties, and then we look at the uncertainties on the unlabeled data, and we say, oh, okay, well, where is the uncertainty greatest? And then you take the data point where the uncertainty is greatest, and you go and do the expensive experiment. It could be an ab initio calculation, it could be a real physical experiment, and then you use that to retrain the model, and the model should become more general. And yeah, this is just a kind of a schematic showing how the approach actually works. And then this is a test of training the model two different ways. So on the green plot, what we're doing is we're updating the model each time with data samples chosen by the active learning process, and the orange one is by just randomly choosing the next example. And we see that the active learning does a much better job at improving the model with less data. Now, I would say this is not optimal at all. I don't think our models are as well calibrated as they could be, and we're doing work to make them better. So I think there's actually potential for this to lead to even better performances and with limited data. So okay, quick summary. Hopefully, machine learning models are not necessarily impenetrable black boxes. Opening them up allows us to understand how to augment them and understand them. And explanations and confidence intervals are really important for being able to trust and use machine learning data. And I just quickly, before the end, I wouldn't get away without plugging our new scientific machine learning benchmark suite. So this is just something slightly different. But the scientific machine learning group has been developing a benchmark suite, which is for testing machine learning methods for scientific applications. So you normally get it and you download some hand-drawn digits and train your models and so on. This is to do the same thing, except with scientific data, so you can test your models on that. So check it out here on GitHub, and it can be easily installed and run. So finally, thank all of these various people, and thank you very much for listening.
Right.